So, preparing aldehydes and ketones. Prepared by the controlled oxidation of alcohols. So what is a controlled oxidation? We know oxidation at this point in terms of burning, right? You combust something, you oxidize it, you burn it. You turn the carbon into carbon dioxide, the oxide of carbon, and you turn the hydrogen into water, the oxide of hydrogen. But that's an uncontrolled oxidation. When you burn something, you're tearing a molecule apart, you're sending oxygen molecules in that you've torn apart. You let the oxygen atoms stick together with the carbon and the hydrogen, you get the oxides, and bang, you've done it. It's crude oxidation. It's like trying to fix something minimalistic. It's like trying to fix your computer with a sledgehammer, right? Kind of a silly thing. Don't mind that. So, combustion is oxidation, but it's like crude oxidation. You're destroying everything, and you're kind of mashing everything back together as carbon dioxide and water. What we want here is a controlled oxidation. In other words, we want oxygen to carefully do its job. And we don't want the oxygen to do the job on the entire molecule. We just want the oxygen to do a little job on a piece of the molecule so that we can change the way oxygen is connected to carbon, right? Because oxidation of an element is all about making connections with an atom with oxygen. You're making connections with oxygen. You're giving up your electron either to oxygen, or you're sharing your electron with oxygen. And remember, oxygen is very electronegative, and so oxygen is a hog when it comes to sharing electrons. It doesn't share very good, right? Right? Other than fluorine, oxygen is next. It's an electron sucker, is what it is. So that's what oxidation is, making connections of other atoms with oxygen. And the more connections that you make, the more oxidized it is, okay? So in organic chemistry, oxidation means the addition of oxygen to an organic molecule or the removal of hydrogen, which is kind of a strange way of looking at it. But when you take away a hydrogen, it always results in more connections being made with more electronegative elements, and that results in this oxidation. If we're not burning it, we need to carefully add oxygen, and so we need chemical compounds that have oxygen in them so that they can just carefully add that oxygen to the molecule without completely destroying it like when we burn it. Some good chemicals that we use, potassium permanganate. You'll notice 4 oxygens in it. This purple liquid right here is potassium permanganate, and I'm going to use that to show you the oxidation of some of these alcohols here. This is potassium dichromate. Again, lots of oxygen in it. Hydrogen peroxide. Hydrogen peroxide carries an extra oxygen around, right? It can release that oxygen and it can do its thing. In the following reactions, instead of writing O2 when we talk about oxidation, I'm going to just write an O. I'm not going to put in the entire chemical, potassium permanganate or hydrogen peroxide. We'll just represent it as an O. So you'll be able to distinguish whether I want a controlled oxidation or not by whether I have an O or an O2 in the formula. All right? Okay, let's go over some of these examples here. Oh, one last thing. Let me just show you what I'm talking about in terms of connections of hydrogens. Oh yeah, yes I can. Thank you. So let me just show you something here for a moment. So when we started talking about hydrocarbons, the first thing we talked about was just a regular hydrocarbon like this, all full of H's. I'm not going to draw the H's in, but all full of H's. And we say it's saturated, okay? And this is an alkane. And then we added an oxygen to it, all right? It doesn't matter where we put the oxygen, but we added an oxygen and we stuck it in between an H, right? This is our alcohol. And you'll notice when we did this, I created one connection. There's one connection there of the carbon with the oxygen. That means this carbon right here is a little more oxidized than this carbon right here because it has one connection with oxygen, okay? Now, the next thing that we looked at was the ethers. And you might say that it's a little more oxidized, but it's actually almost the same oxidized. If I have then my carbon and my oxygen and my carbon, each of these carbons, again, has one connection with oxygen. So this has two carbons that are kind of oxidized, where this has one carbon that's kind of oxidized. So you might say that this is a little bit more oxidized than this one. Not much, though. Now, the next thing we encountered was the aldehyde or the ketone. And it doesn't matter which one I draw. In an aldehyde or a ketone, and I'm going to use the ketone, we now have this scenario. Notice we've taken an H off of the O, and we've made that extra electron come around and make an extra bond. So you'll notice that this carbon right here now has two connections with oxygen, which means it's a little more oxidized than this, because it's now losing a pair of electrons to that hog of the oxygen atom, which it is. It's going to suck those electrons away, where this guy only loses one electron as it sucks the electron away from the carbon atom. Now, the most oxidized form of carbon is carbon dioxide. And if you take a look at that, it has four connections with oxygen. Every one of its electrons, every one of the four outer electrons is being sucked away from the carbon atom, which means carbon dioxide is the most oxidized form of carbon that you can have, where the carbons in this are the least oxidized form of carbon that you can have. So we've been moving towards increased oxidation, all right? At the end of today's class or tomorrow, we're going to look at what are called carboxylic acids or esters. It doesn't matter, but they look like this. It has a carbon that's doubly bonded to an oxygen and then singly bonded to another oxygen, and then either more carbons or hydrogens. It doesn't matter what goes on the end. But you'll notice this guy has three connections with oxygen. That makes this carbon even more oxidized than a ketone and an aldehyde. So as you increase your connections with oxygen, right, you end up with it being more oxidized, we say, all right? And here we've got less oxidized, all right? That's why we can get lots of energy out of these molecules, because they're not oxidized at all. And when we combust them, bang, we go all the way over to here. Crude oxidation, tear everything apart, stick oxygens on it. But what we want to do today is we want to go from here carefully over to here. We want to increase that oxidation by one little step, all right? Okay? All right, so that's a good way of thinking of oxidation in organic compounds. We're really thinking about the number of contacts that our carbon has with oxygen. So here we've got a general equation, and then we'll do some specific examples. If you take an alcohol, all right, there's our general formula for alcohols, R representing just a bunch of carbons, and you do what we call a mild oxidation. You'll notice I've represented it as an O in brackets. That's not an O2, right? We can combust an alcohol. If I wanted the combustion reaction, I would have put an O2 in this position. But on a test or an exam, if I give you just an O in brackets, then that'll signify to you we just want a careful oxidation. So if we do a mild or a controlled oxidation, we can turn our alcohol into an aldehyde. When you do that particular maneuver, you always also get a water molecule. Even though water is formed, this isn't a dehydration, this isn't a condensation. This is an oxidation reaction. So water, you'll notice, is a product in a lot of reactions. So how does this work? And I'll show you in a moment. But what takes place is this oxygen actually removes an H from the alcohol and an H from the key carbon. And we'll look at those examples. And it actually draws the waters out. In this case, we don't use sulfuric acid as a catalyst. In some subsequent reactions, we will. The one tomorrow, if we do the activity, we will. But in this one, you don't need that. So an alcohol, mild oxidation, using one of those chemicals we mentioned on the previous slide. Here I've got some potassium permanganate. And when you do that, you increase the number of contacts of the key carbon with the oxygen. In other words, we oxidize it. So let's go over some examples. So oxidation of a primary alcohol. In this case, I'm using ethanol. It's a primary alcohol because my OH is on the end carbon, and the key carbon is only connected to one carbon. All right? And controlled oxidation. Now, as we go through these, I'm going to show you some demonstrations as we go along. What I have in here is N-butanol. That means it's regular butanol, 4 carbons, with the alcohol on the end. This is a primary alcohol, except it simply has 2 more carbons than this one. I'm going to add 3 drops of potassium permanganate to that. And potassium permanganate is a good chemical to use here because it's very purple. It tells us that the potassium permanganate is existing as the purple color. When the potassium permanganate is used up, in other words, when the oxygens are removed, it turns to kind of a yellowish brownish color. So that'll indicate to us whether the oxidation has taken place or not. Now I'm going to add 1, 2, it looks like I got 3 in there. And I'm going to mix it up. And then I'm going to let it sit because the oxidation takes a little time to take place. So there you can see the purple color is in there. I'm now going to put that back down, and I'm going to let it do its thing. And we'll come back to that in a moment. All right? So the purple is the potassium permanganate. And if all the oxygens are used up on them, then it becomes a different color. All right? Let's complete this reaction first. So here's what happens. This oxygen essentially takes a hydrogen. Whoops, I'm not getting any colors here. Essentially, and it's failing me. It's going to fail me today. Right in the middle of all this garbage. I usually test it every time. I hate this piece of machinery. Unbelievable. I always have to escape right out of it. I would like to say something. I got to have this work, so I've got to reload. second. Nah, it doesn't. The smartboard isn't connected. Okay, we got it. We got to figure it out. Okay, here we go. So this is the way it's functioning. We have, and that's still not going to write. That's absolutely crazy. I got to use this. This is going to be a little ugly. We have the H from that one, and the H from that one, and it connects to the O like this. All right? So in a controlled oxidation, this oxygen right here, okay, pulls an H off of the alcohol and an H off of the key carbon. All right? Which then is going to result in, oh, this is going to be ugly, folks, CH3. This is classic writing with the mouse. That's going to now give me a double bond right there on that guy. I still have one H left. You see how there's an H left there? That results in an H on the side there, okay? And H2O. H2O. That's not bad. It's a little scary, but it's scary that I can actually do that. All right. So our ethanol, our primary alcohol, and now I've lost the ability to write. No, there it is. Our ethanol becomes, what's this stuff going to be called? 2 carbons. I've got my carbonyl group at the very end. So what is this stuff if the carbonyl group's at the end? What's that? It's ethanal. Yeah, it's an aldehyde, right? Remember the carbonyl group's at the end. That's ethanal. Ethanal. And I don't know if we've got any action happening over here. Yeah, you can see there we've gone from a purple color to a brown color. So that's successfully been oxidized. Okay? One last little thing that's going to come with this little note here. Oxidation of a primary alcohol produces an aldehyde. And that's because with the OH on the end carbon, it makes your carbonyl group, C double bond O, also on the end carbon. And that's probably why the professor told us that a primary alcohol has the OH on the end carbon. That's the convenient way for this to remember this. If the OH is on the end carbon, then when you do a mild oxidation to make it into the aldehyde, you always get the aldehyde. You always get it on the end. All right? You get your carbonyl group on the end. Okay? Let's take a look at, the 1-butanol. I'm not even going to worry about it. I'm doing it as a demonstration, but I do want to keep going. Let's look at it for a secondary. I also have a secondary alcohol here in our demonstration. It's 2-butanol, all right? It's the secondary version of the butanol. And I'm going to put some potassium permanganate into that and get that reaction going. Again, because it takes a little bit of time. So again, I'll add 2 or 3 drops. 1, 2, I added 3 to the last one, so to be a little bit consistent, we'll add 3 there. And I'll give that a shake. And you can see there, that purple disappeared almost instantly. That was highly reactive compared to the other one. The other one took a little longer, but that purple color disappeared right off the bat. So that definitely successfully resulted in an oxidation reaction. The oxygen in the potassium permanganate was used up. So let's take a look at this one. So this one, notice the key carbon, I've got that hydrogen right there. That's going to go with the oxygen. And again, it's a hydrogen off of the key carbon that's going to go with the oxygen. Okay? Which is then going to bring a bond down here. So we take 2 hydrogens off, one of the alcohol, one of the key carbon, and that leaves me with a space to put the double bond. CH3, C. Now I've got the double bond to the O because we've taken that H off of it. And then CH3, and we still have our water, H2O. And what is this stuff called? Doesn't have the carbonyl group on the end, so it's not an aldehyde. It's a ketone. It's propanone. No number needed on that one. We just discussed that, right? It's that one right there, right? Uh-oh, I'm losing it here on the mouse writing. Propanone. Propanone. What's that? No, it doesn't, because it can only be in the middle. It can only be in the middle. That carbonyl group can only be in the middle. Oh, propanol, it does have to have the number designation, because I could have one propanol, right, which would then result in propanal. That's another way of thinking of it, right? If you have something greater than ethanol, and it's got a number on it, and it's an alcohol, and it's got 1 on the front, it'll become an aldehyde, because it's primary, right? So one propanol would become propanal, and 2-propanol becomes propanone, because it puts it in the middle, okay? Because that's where the OH is. All right, so essentially, secondary alcohols become ketones. So primary alcohols become aldehydes, and secondary alcohols become ketones. And they're doing sound experiments, because I can hear the tuning forks. That's what that was. Wasn't sure what it was, but it's tuning forks out there. Yeah, columns, yep. Well, logically, we're going to have to discuss what takes place with tertiary alcohol, because we've obviously taken care of primary and secondary. That's the reason why I have to teach you about the different types of alcohols, because it explains how we make these things. So last I have, and we're not going to worry about the 2-butanol. I've shown it to you here. I've shown you the reaction. Let's now take a look at a tertiary alcohol. And this is actually the alcohol that I have. My next example is the container we have, it literally is called tert butyl alcohol. It's another way of saying tertiary butyl alcohol. It's another naming system, tert butyl alcohol. It's a tertiary alcohol that has 4 carbons, and that's exactly what we have here. 1, 2, 3, 4 with an alcohol on it. And it's tertiary, so it's a propanol in the number 2 position with a branch in the same position. Remember we talked about that a couple days ago? That's how you can tell whether an alcohol is primary, secondary, or tertiary. Primary, it's got to have a number 1, right? Secondary, it's got to have a number 2 without a branch with the same number. Tertiary, it's got to be a number 2 with a branch with the same number. So that's a tertiary alcohol. Now, remember, in order for the tertiary, or in order for the alcohol to be oxidized, I need to take an H from the O, but I also need to take an H from the carbon, the key carbon, so that I can make that double bond. And you'll notice there is no H on the key carbon. It won't pluck off one of these. Therefore, this is no reaction. No reaction of a tertiary alcohol. We say that it's not readily oxidized. We could burn it, right? We could blow this thing apart and we could turn it into carbon dioxide and water, but we cannot do a nice little oxidation. Let's demonstrate that one. So if it doesn't use up the oxygens that are in the potassium permanganate, 3 drops, then our purple color should never disappear, because that means the potassium permanganate is still going to exist in its form. And, well, it's definitely not as quick as the other one, but that other one took some time. So we'll leave this and we'll take a look at it in a minute. But ideally, if everything's correct, it shouldn't change color. All right, we shouldn't lose that. All right? And so that's how we oxidize alcohols in order to make ketones and aldehydes. Let's do an example. No, we're not going to worry about that one. No, we'll go on to the next reaction. We'll go on to the next reaction. I wasn't going to do that example. That's that one right there. So that's how we produce aldehydes and ketones. Now we want to talk about how we can reverse that reaction and make them into alcohols. And it's simply an addition reaction. As you're writing that and getting ready to do that, I do have a fourth alcohol that I found in the cupboard. I thought, what the heck, I'll just grab one. This is actually a way in which we test for different types of alcohols. We can do a quick test of whether it's primary or secondary versus tertiary, whether that purple disappears. This is called, why didn't I write it down? It's terrible. I should have labeled it. This is isobutyl alcohol. Iso describes a way in which the carbon atoms are connected, and I haven't taught you the iso prefix. To be honest, I'd have to look it up to determine whether this is primary, secondary, or tertiary. So I really don't remember. So let's put some potassium permanganate in it, and let's take a look to see if we get a color change or not in a little bit. So again, it's an alcohol. I'm not sure whether it's primary, secondary, or tertiary. 1, 2, 3 drops. And we'll mix it up, and we'll let it sit here for a while. So it's looking a little purpley there at this point. Let's put it right beside that one. Let's let it sit for a little bit. We'll come back and see if we can identify whether it's primary, secondary, or tertiary by that little test. Okay. Continuing on. We can do the exact reverse reaction that we just did by doing an addition type reaction. All right? Now, this reaction doesn't happen readily. It needs some pressure and we need a catalyst, but it can be done. This is the exact kind of reverse of what we just did. In this case, one of the hydrogens sticks onto the oxygen, and I didn't mean to drive it through there like that. The other hydrogen attaches itself to the key carbon, and we get our alcohol back. In the previous reactions, we essentially removed 2 H's by having the oxygen pull it off and turn it into water. In this case, we're putting the hydrogens back on. It's just like an addition reaction on a regular double bond. Remember how we had the reaction for a regular double bond, and we added H2, and those H's were essentially added on to the carbons? We broke the double bond. This is the same situation, except we're adding 1 H to an O and 1 H to the C. That's flanking the double bond. It's the same type reaction, okay? It doesn't happen as easily. It takes high pressure and a catalyst. This happens pretty easily. We did that in that little reaction. It's actually still sitting in the beaker over there, where we added some of that, what did we add to it? Iodine. We added the iodine to it. Happens quite easily. Okay, so this one we're getting back our CH3. We've got C. We've turned it back into an OH. It's got a single H on it now because that came from the hydrogen. And actually, we already had an H, so it's now got 2 H's on it. And that took our ethanol and turned it back into ethanol. We just reversed it. Okay? So we can add hydrogen back on across that bond. I don't think we need to write that. Hydrogen adds across the double bond between the carbon and the oxygen. I think we've got that information. Okay. Hydrogenation of an aldehyde produces a primary alcohol. You can write that one down. That's a good thing to put right in there. Because we can do the same for a ketone and we'll get a secondary alcohol. Oh, that's exciting, right? That means this was a primary or a secondary alcohol. It looks the same as this. I don't know whether we can conclude it was primary or not from that, but it's definitely a reaction. So that isobutyl alcohol would be secondary. What's that? Yeah, it isn't a tertiary. That's what we can conclusively say at this point. We'd have to do a little more checking on that to see if we could go by the color of one being an aldehyde and the other one being a ketone. Maybe there is. Okay, so let's keep rolling here. And essentially here, we're going to end up with hydrogenation of a ketone produces a secondary alcohol. So again, this guy onto there, this guy onto there. When you do reactions on a test exam, I don't need to see the arrows, but if you want to put the arrows to help you think it through, that's no problem. So now I'm going to have my CH3, C, and now there's an H attached to it. I got an OH there, and I got a CH3. So my propanone becomes 2-propanol again. And I'm not going to try to write that with my mouse because it's really just painful. This is propanone, right? And this is 2-propanol. Yeah, so if you want to write that in, by all means, I'm not going to do it because my mouse writing is sad. So hydrogenation of a ketone produces a secondary alcohol. Essentially the reverse reaction of the controlled oxidation. Okay? Here we've got some practice problems. Let's just move on and talk about the carboxylic acids and esters. The practice problems are the same type thing. You can do them for homework, and we're pulling them off and we're moving them.